Welcome back, guys. We will continue with part 3 of the exponential handout. In this video, I will be talking about the exponential expressions and how to graph it. So the general form would be y equals ab to the power x, where the x and a are real numbers and a cannot be 0. Because if you take a look at the function and if the a is 0, then your function would be y equal to 0, which is not possible. And the b, it's also part of a real number. It should be greater than 0, and it is not 1. It shouldn't be equal to 1. And b is called the base. So if I want to write down all the conditions, you know that a and x, they are part of the real numbers, okay? And the b is also part of the real numbers, but there are some other extra conditions for b and a. First of all, b should be greater than 0, okay? b, it's not 1, never 1, and it's also called the base. The a, as I just mentioned, it's not equal to 0. Now, in the previous video, we talked about how to change from one base to another, converting the base, but I will just go over a couple of more examples and then show you how to do it. So let's say in here, I have this thing 81, okay, 81 to the power 3x, okay. Now what I want to do, I want to convert it to the base 3. Here the base is 81, but I want to change it to 3. And I want to calculate what would be the new base, okay. So 81 is actually 3 to the power 4. If I substitute 81 with 3 to the power 4, it will come up to 3 to the power 12x. So this side, in this square, I should put 12x. In the previous video I posted, there are some examples. You can go over them and try to solve them. I wouldn't go over any of those again. I will leave you to it to just solve it. What I want to do in the rest of this video, I want to solve some exponential equations. In order to solve the exponential equations, it is important to be able to change or convert the bases. Let me give you an example so you will get an idea what is an exponential equation. So let's say 3 to the power. It's on page 6 of your handout, 2x plus 3, okay, equal to, on the other side, I have 3 to the power 5. This is the exponential equation, and you have to find the x. Here, if you want to solve an exponential equation, the first step, if I want to write it in a few steps, the first step, make both sides same base. So you should convert one of the sides or two sides to a common base. Okay, then the step 2 is to equate the power, right? This is step 2, and step 3 is to solve for x. When you do step 2, you can either find a linear, quadratic, it could be any equation. And in step 3, you just have to solve the equation. Okay, so here, for this specific question, let's do it together and see how we can find the x. Step 1, we have to make sure both sides have the same base. The good thing is here, both bases are 3. So we just have to equate the power. 2x plus 3, it must be equal to 5. From here, 2x must be equal to 2, and x is 1. Right? And this is the answer. That's a very straightforward one. We always start with the simple one, and we move to intermediate and then the advanced questions. Okay, next question is 5 to the power 5x minus 1. Now this is the second equation. Let's solve it together. Here, as you can see on this side, the base is 5. On the other side, it's 125. So in the first step, we had to make sure that both sides have the same base. We know, as a side note, 125, it's 5 to the power 3. Okay, so instead of 125, I just write 5 to the power 3 to the power 4x must be equal to 5x minus 1. Then the two bases are equal. That means the power should be equal. So let's simplify it. 5x minus 1. On this side, 3 times 4x is 12x. Then the two powers should be equal, 12x. And you end up with a linear equation. And if you solve this linear equation, the final answer would be negative 1 over 7. That's the final answer. Okay, next question. It's 7 to the power 5x equals 343 to the power 3x plus 2. Again, here the two bases on the both sides of the equal sign are not the same. So we have to convert one of the bases or both of them depending on the situation, so that we would have the same base on both sides of the equation. Here, what I know is 343 is actually 7 to the power 3. Okay, so now what I'll do in the next step, I simply substitute 343 with 7 to the power 3. Now it's 3x plus 2. Okay, from here the bases are equal, so now the powers must be equal. So 5x is equal to 9x plus 6. And then if you solve this linear equation, you will find the final value of x to be negative 3 divided by 2. Moving on to the next example, on this side we have 2 to the power x multiplied by 2. On this side I have 64 and then a square root of 2. First of all, 64, it's a different base. We have to make it the same base. So 64, we substituted with 2 to the power 6. If we substituted with 2 to the power 6, we would have the same base on both sides of the equation. But before equating the powers, we have to simplify each side. Okay, so this side would be 2x plus 1 because this is power 1, right? And when the two bases are equal, the powers would be added together. On this side, as a side note, you would know that the square root of 2 is 2 to the power half. So I just substituted 2 to the power 6 and 2 to the power half. Again, this would be 2 to the power 6.5. Okay, and then you could say, hey, right now I can equate the power. So x plus 1 must be equal to 6.5. And the final value of x would be 11 over 2 or 5.5. I changed my pen to write down the new question, so you wouldn't confuse it with the previous one. I'll just write the solution in blue. So the next question, you have two different bases, but if you look closely, you can find the relationship between these two. So let's say 949, you can write it as 3 over 7 to the power 2, right? And if you compare the two sides, 3 over 7 and then 7 over 3. So one of them is the reciprocal of the other one. So what I can do here, I will just reciprocate this one and then negate the power. So on this side, Okay, now let's solve this one. Here we had negative x from before, so negative 2 times negative x would be plus 2x. So now we can equate the two powers. 2x equals to 2x minus 2, which, okay, if I move it to this part, so that would be 0 equal to negative 2, which is not possible. So this is not possible. That means, okay, so this is how you should write it. So this is impossible. So that means there is no solution for this equation. Okay, the next one. Okay, now the next question here again, you would see that you have 2 on both sides and 128. I guess you can change it, and you definitely can. You can definitely change it to base 2 to the power 7. Okay, now I substitute everything, and then after simplification, I just leave it to you. I just jump 2 steps together. So that would be 2 to the power 3x minus 1. On this side, I would have 2 to the power 21x from here plus 3x from here. So now the bases are equal. What I have to do, I have to equate the power. So 3x minus 1 must be equal to 24x. And from here, if you solve it, the x would be negative 1 over 21. Okay, now next page, we move on to the homework. I want you to please solve these ones and then watch the video. Next question, which part of the homework? Letter G. So here we have a combination of 3 different bases, 1/4, 2, and 32. But you know that 4 and 32 can be written as 2 to the power something, and then you can use the rules of exponential to convert all the bases to 2. So as we know, 1/4 is 2 to the power negative 2, right? So I just substituted 2 to the power negative 2 and then x to the power negative 8. On this side, I have 2. 25 is 2 to the power 5, 2x plus 3. Then you have to simplify. This side will be multiplied by this, negative 2x plus 16. And on this side, you have 10x here. Then you have 15, and then you have 1 here, which is 16. So the bases are equal. That's perfect. We just have to equate the two powers, which is 10x plus 16. We end up with a linear equation. And if you solve this linear equation, you will see that the x is 0. X is 0 is your answer. Okay, next question. This question is super important. I want you to just pay attention to this question. Here I have a fraction, and then there is the third root. On this side, I have 9. So in order to solve this equation, remember, the first step, we have to come up with a common base. Here we have 3, 9, and 27. So I would say the best bet would be 3. 9 is actually 7 to the power 2, and 27 is 3 to the power 3. Okay, so I want to get rid of this sign and write it as an exponent. So 27, 2x minus 1 over 3x plus 1. And instead of this sign, I will remove that one and use 1/3 as a power. Okay, next step, this side is 3 to the power 2. Okay, so now I'm going to do each one separately. Let's deal with this thing. 27 to the power 2x minus 1. Okay, 27, 2x minus 1. It's 3 to the power 3. Okay, 2x minus 1. It would be 3, 6x minus 3. Okay, and remember, when the fraction, everything it's inside a bracket and there is an exponent or power outside. So this power belongs to the numerator and denominator. Okay, so here I will just substitute what I calculated here. So that would be 3 to the power 6x minus 3. But remember, I have an exponent or power sitting outside. So I'm going to write it with a different color. Okay, 1 over 3. On the denominator, I have 3 to the power x plus 1. And then it is 1/3. Perfect. Okay, so now let's make it a little bit simple. This 1/3 will be simplified by this. So that would be 2x minus 1. And then here I have on the denominator, 1/3 should be multiplied, right? So okay, so 1/3 would be multiplied by this. Now what I'm planning to do in the next step is to move everything from the denominator to numerator. But remember, when we do this, everything would be like the power would be multiplied by a negative sign, right? Okay, the next step would be adding the exponent because all of them have got the base 3. So 2x minus x over 3 would be 5x 3, and then negative 1 and negative 1/3 would be negative 4 over 3. Remember guys, on this side we still have 3 to the power 2. So from here we have to equate the power of 5x divided by 3 minus 4 over 3 equals to 2. Okay, so I have to move everything to this side. 2 plus 4 divided 3. So for those of you who need a reminder, you guys have to do common denominator here. Common denominator is 3, so that would be 6 plus 4, which is 10 to the power 3. Okay, so from here you should say 5x divided by 3, it's equal to 10 to the power 3. So take a look at here. You have two fractions, one on each side. Both of them have got the same denominator. So you could say same denominator. So I could say 5x must be equal to 10. From here, x is equal to 2. That was a very nice, interesting question. A typical question that you will get in the test. The next two questions are also amazingly interesting. This question, and the next two are the typical question that you will get for your final. Because you will see it will challenge you and it will need your knowledge in not only exponential but quadratic and other general knowledge of math. So here, let me write the question. Okay, if you take a look at here closely, you would see that this equation is kind of similar to our quadratic equation, right? We have a constant, we have like something to the power x and something to the power 2x, right? So here we would change, I will give you the hint. So here we would use change of variables. So let's say we say 7 to the power x, we use a different variable for that. We just call it t for now. That's the intermediate variable. So if t is 7 to the power x, t to the power 2 would be 7 to the power 2x. Okay, so now let's go back to our equation and substitute. So here your equation will change into 2t squared minus 7t minus 15 equal to 0. And this is a typical quadratic, right? So to solve this quadratic, you can use the quadratic formula or you can use factorization. It's up to you. I will use the factorization. It will factorize to 2t plus 3 and t minus 5 equal to 0. So again, when two brackets or multiple brackets are multiplied by one another and the answer is 0, any of those brackets is a potential 0. So here t could be 5 and here t could be sorry, negative 3 over 2. Okay, so you have two answers, but the two answers are for t. Now we have to, from t, we have to get to x. Okay, so now we have to solve for x. Okay, so if your t is negative 3 over 2, that means 7 over x is negative. From here, we solved for t. Now we go and solve for x, because remember the t was the intermediate variable. So t is negative 3 over 2, and remember t is 7 over x. So negative 3 over 2 is equal to 7 to the power x, which is not true, and you will see later. Okay, because 7 to the power x, it's always greater than 0. So this one, okay, so t equal negative 3 over 2, it's a rejected answer. Okay, now what about the other one? So here you have to say your other answer, t is equal to 5, 5 is equal to 7 to the power x. That's a correct answer. You will see how later you can solve for this one, but this is a correct answer. From here, you can get the correct answer. Okay, this is another example which reminds us of quadratic equation. Here we use the change of variable again. This time we use 3 to the power x as t. So 3 to the power 2x, or in other words, 9 to the power x is called t2, right? So if I replace it here, the answer would be 6t2 minus 11t plus 3 equal to 0. Okay, this is the equation, quadratic equation. Let's solve it by quadratic formula. A is 6, B is negative 11, and C is 3. Now I just substituted in the quadratic formula. Plus and minus 121 minus 4 times AC, which is 18, 2 times A, which is 12. So the answer would be 11 plus and minus 121 minus 72. Okay, so 49 and then 12. So we get two answers. One of them is 11 plus 49 divided by 12, and the other one is 11 minus 49 divided by 12. So here it would be 60 over 12, which is 5, and here would be minus 38, okay, divided by 12, which is minus 19 over 6. So these are the two answers you got so far for t. Remember, t is equal to 3 to the power x, right? 3 to the power x. So from here, you should be solve for x. We will continue and see how we can solve for these type of equations. To solve for x, we have to use logarithm. As we haven't explored this topic yet, I will leave it like this for now. We will continue with the exponential function about the basic characteristics of the graph. And then when we learned about the logarithm, we will see how we can solve these type of questions. Okay, as I just mentioned, we're going to talk about the exponential function. As you know, the definition is, I just put it here, y equals a times b to the power x, or sometimes instead of y, if you look at some textbook, they go as f of x. That means function in terms of x, because your variable here is x. And remember, b, it's always the base, right? In the beginning of the video, I just mentioned that the x and a can be any real number, and a cannot be 0. And the b is also a real number, it's greater than 0, and it's not equal to 1. But remember, whenever we talk about the function, we have to talk about the characteristics. So here we will talk about the domain, range, the x-intercept, and the y-intercept, and also the asymptotes. These are the important characteristics of any functions. So let's start with the domain. Now let's do a reminder as a side note. What is a domain? If you remember, the domain of the function, it's a complete set of possible values of the independent variable. And here your independent variable is x. So domain always refer to the x values, okay? So in other words, the domain, it's the set of all possible x values which make the function work. Or these are the values which are permissible. If I do a little graph here, I will show it later to you, of the ex, the exponential. So here it's x value, here it's the y value, and here it's 1. And my function, it's y equal e to the power x, exponential of x. So this is going to be your function, right? This is the general shape of an exponential. And remember, the domain always refers to the permissible, or the values of x that your function can take. And here, if you take a look at here, this pink graph goes to negative infinity, and from the positive side, it goes to the positive infinity. So in other words, if you want to find the, talk about the domain of the exponential graph, the x is all the real numbers. Okay? Now, let's talk about the range. When we talk about the range relates to the independent, or the y value. Remember, when we talk about the range, we're talking about the permissible y values. Okay, here you would see that the y can take any number, but it's never negative, right? It's always positive. It's not even 0, so it's greater than 0. Okay, so this is your domain, this is your range. And now let's talk about the x-intercept. Okay, so the x-intercept, it's when y is equal to 0, right? And if we want to solve this equation, that means abx is equal to 0, okay? And remember, we had this condition that a cannot be 0. So in other words, if we want this function to be 0, like equation to be 0, this must be 0, which is impossible. So in other words, it means there is no x-intercept, right? There is no x-intercept. Because if you remember, the b, it's always greater than 0, and b, it's opposite of 1. Okay, So there is no x-intercept. If you find it difficult to remember, you can always graph the exponential function or have this exponential function in your mind. Then from there, you could easily see that there is no x-intercept. But how about the y-intercept? For the y-intercept, in other words, the x must be 0. Okay, so y equals ab to the power x. So from here, that would be, okay, so it would be b to the power 0, so that would be a. Okay, so this would be your y-intercept. But let's talk about the asymptote. I think most of you haven't heard about this before, or you didn't have enough practice. So let's talk about the definition. Then we talk about the asymptote of an exponential function. So by definition, an asymptote is a line that any curve approaches, but it never touches that line. Okay, so we could have vertical or horizontal asymptote. Let me give you an example here. Okay, so if this is as a side note, okay, so I'll do another graph here for you guys, and you will see that this graph, let's say this is also an exponential, right? But then here, let's do this line, and this is point B. So I didn't do a very good job, but this orange curve should never and will never touch the pink line. They actually get so close, but they never touch, and it's called an asymptote. And this is, as you can see, a horizontal, right? This is an horizontal asymptote. But we can also have vertical asymptote. So take a look at here. If for the same graph, I'll just do, let's call this point C. And if I continue this graph like this, so this graph goes up, 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 but it never crosses point C. It gets so close to point C, but it never, never, never crosses it. So this line, the vertical line, okay, it's actually the asymptote. And if you remember, if this is like if you consider the, so talking about asymptotes, I want to do a reminder for you guys as a side note. So asymptotes are straight lines that constantly approach a given curve, but it doesn't, meet the curve. They get so close, but the curve, which is like this orange one, and the line, the pink line or the brown line, they never, pass each other. So let's say this is my curve, the orange one. It could be any given curve, and I have a horizontal line and a vertical line. This is the equation of the horizontal line, y equals to b, and this is the equation of the horizontal line, x equal to c. These are the two asymptotes. As you can see, this is the vertical asymptote, this is the horizontal asymptote. So the curve gets so close, but they never actually touch one another. Back to our discussion about the asymptotes of the exponential curve. If you want to find the horizontal asymptote, right, horizontal. So the horizontal asymptote, the equation would be y equals to b, right, or d. It could be any number. So here, if it's equal to b or d, then we have to simply substitute it. So here, remember, the asymptotes, it's when we go toward infinity, right? At the very end. So here, if you want to be generalize it, for this exponential graph, which we had up here, the asymptote is when our x goes to negative infinity, and then the curve gets so close to it. So it gets so close to the x axis. And as you know, the equation for the x axis, it's y equals to 0. But if we want to consider all the general forms, our exponential could also be elevated. So we would consider, right? We would consider y equals to d to be an asymptote, which d could be 0 or any other number, right? For the vertical asymptote, on the other hand, okay, vertical asymptote of the exponential function. In order to find the vertical asymptote, we refer back to the shape of the exponential function. This is an exponential function, right? So this guy can go forever and ever, and you can see that you cannot define any line which is the end or the dead end. Like this guy can go forever and ever. So for vertical asymptote, there is no vertical asymptote, right? Remember, guys, this graph which I gave you, it was only for explaining the asymptote. Otherwise, the graph for an exponential function is this one. Okay, now let's talk about graphing, which is very useful, especially when you're introduced to a new type of function. Try to see different types of different graphs of it with different coefficients, and see like how does it look like, how the shape is changing in regard to changing the parameter, and what are the range and domain of the function. So here we start with a very simple common exponential function, which is y equals e to the power x. We want to draw it and see like how it's look like. Okay, so let's start. Remember, for any function, if we want to graph it, right, we just go like this. We go x, y, x is 0, x is 1, x is 2. If I put as x as 0, the answer would be 1. If I put x as 1, that would be e to the power 1, e to the power 2. And you can put these values in your calculator and get the value. Then we have to just create our x and y axis. Okay, let's create my x and y axis, and we locate the points and connect them. Okay, so this is your y, this is your x, right? And now the values would be okay, so this guy would be something around 2.7, and e to the power 2 would come up with 7.38. So 0, let's call it 0, 1. The other one is 1, and then 2.7. 1, 2, 3. So it should be something around here. 2, and then 7.8. So this is 3, 4, 5, 6, 7, and here. Okay. So now I found 3 points of my curve. I can connect them. In order to get a more accurate one, I'll go with some negative values for x as well. So it gives me an idea. So negative 1, which would be e to the power negative 1, which is 1 over 2 to 2.7, which would be 0.36. And if it's negative 2, it will come up to 0.13. So negative 1 and 0.3. So this is 0.3, and negative 2 and 0.1. See, it is getting closer to the x line, but even if you give it like very big numbers on the negative side, if you do a perfect graph, it will never touch. So let me just see if I can use another pen to just do the graph. So remember, this is a curve. It should never touch the x-axis. It gets so close to. So this is y equals e to the power x. Awesome. This is the general shape. This is only e to the power x. And remember, your exponential function can have a coefficient. So sometimes they could give you like 2 times e to the power x. 5 times e to the power x, right? But this is the general shape you will get. Now, the next part would be talking about the domain, the range, and then the asymptotes, right? So, as we discussed, the domain of the function, right? It's R. Okay, now how about the range, right? R stands for the range and F stands for the function. So here, as you can see, your function is not defined in the negative values of Y. So your range is any value for Y greater than 0. And remember, the Y could be any number, like any of the real number. How about asymptotes? So if you take a look at here, the asymptote, we have a horizontal asymptote. It gets so close to the x-axis, but it never touches it. So y equals 0, it's a horizontal, right? Horizontal asymptote. The next two parameters we have to always define, it's the x-intercept and the y-intercept. If you take a look at the graph for the x-intercept, it's defined where it passes through the x-axis, which is it never passes through the x-axis, so there is none. But for the y, remember this point, there is a y-intercept. There is a point where the curve actually passes through the y-axis, and it is exactly as point x equal to 0, and the y value would be e to the power 0, which is 1. This is the y-intercept. Okay, so remember, whenever I give you, like in the exam or the test, whenever you're giving a function, okay, and you're asked to do the graphing, you have to create this table with the exact values, then you graph it. Most probably you will be asked about these parameters, which are the domain, range, asymptote, x-intercept, and y-intercept. And for all of those, you have to write like your solution, either your solution, or you have to explain, okay? This is the end of exponential function. I hope you enjoyed the videos and you learned. In the rest of the handout, as you would see, there are logarithm function. These functions are the opposite of exponential function. So I want you to be really good at the exponential before we jump into the logarithmic function, because here then we have to define it, we have to talk about restriction, characteristics, domain, range, equations, and so many other things. So please try to watch the videos, try to do as many questions as you can, and reach out to me if you have any more questions. See you soon.